Welcome to the Introduction to Battery Technology course. This lecture focuses on Chapter 6, which discusses lithium batteries. Introduction to Battery Technology, Chapter 6, Lithium Batteries. This chapter is divided into 3 lectures, and this is the second lecture in the series. Cathode versus anode in LIB operation and manufacturing. This slide explains one of the most important and often confusing concepts in lithium-ion battery manufacturing: how we define the cathode and anode. Even though the roles of the electrodes reverse during charge and discharge, in manufacturing, we always define them by their behavior during discharge, which is the normal operating mode of the cell. That means the cathode is always the positive electrode, and the anode is always the negative electrode, regardless of what happens during charging. During discharge, lithium ions move from the anode to the cathode through the electrolyte, while electrons flow through the external circuit, delivering electrical power to the load. The anode, negative, releases lithium ions and electrons. It's oxidized. The cathode, positive, accepts those ions and electrons. It's reduced. During charging, both flows reverse. Lithium ions return to the anode, and the charger drives electrons back. But again, the naming stays fixed: cathode for the positive electrode and anode for the negative one, to avoid confusion in design, labeling, and production. In manufacturing terms, the cathode is made from lithium metal oxides, like LiCoO2 or NMC, and coated on aluminum foil. The anode is made from graphite or silicon carbon materials and coated on copper foil. Remember, even if the functions swap during operation, the naming never changes in the production line. Cathode versus anode in LIB operation and manufacturing. 2 halves. This slide shows the complete picture of how lithium-ion batteries work, both during discharging and charging, and how the same electrodes appear to switch roles, even though their names in manufacturing stay fixed. Let's start with the discharge process on the left. The anode, negative electrode, releases lithium ions into the electrolyte and electrons into the external circuit. Those electrons travel through the load, doing useful work. That's your battery powering a motor or light. At the same time, lithium ions travel inside the cell through the electrolyte toward the cathode, positive electrode, where they're stored again. Chemically, oxidation happens at the anode and reduction happens at the cathode. Now, on the charging side to the right, the charger forces electrons back into the anode, and lithium ions return through the electrolyte from cathode. This is the reverse reaction. The battery stores energy again for future use. So, in this phase, the anode behaves like a cathode and vice versa, but we keep the same naming convention to avoid confusion in production and system design. The key takeaway: although the electrical polarity changes between charging and discharging, the terminology does not. The cathode is always the positive electrode, and the anode is always the negative electrode in lithium-ion battery manufacturing. Please review this slide carefully and compare it to the previous one. Together, they help clarify how ion and electron movements define the working principle of lithium-ion batteries. Anode of lithium-ion battery. The anode is the negative electrode of a lithium-ion battery and plays a key role in storing and releasing lithium ions. During charging, lithium ions move from the cathode to the anode, where they are intercalated or inserted between layers of graphite. During discharging, those ions move back to the cathode, releasing energy as electrons flow through the external circuit to power a load. The reaction is reversible: Li plus E plus C Li CH6. Graphite is the most common anode material because its layered structure allows lithium ions to move in and out easily, maintaining stability and long cycle life. The anode also includes a copper current collector and binders to hold the material together. Alternative materials like silicon or titanium dioxide can store more lithium, but graphite remains the standard due to its balance of safety, cost, and durability. The diagram here shows how lithium ions travel through the electrolyte and insert into the graphite layers, the foundation of how modern lithium-ion batteries operate. Cathode of lithium-ion battery. This slide focuses on the cathode, the positive electrode in a lithium-ion battery. The table lists several common cathode materials such as LCO, NMC, NCA, LMO, and LFP, along with their key characteristics and applications, from small electronics to electric vehicles and industrial systems. The diagrams illustrate how lithium ions are intercalated into the cathode's crystal structure. The top figure shows the layered structure of LiCoO2, while the bottom one shows the spinel structure of Li-Mn2O4. These structures determine how easily lithium ions can move in and out, affecting the battery's energy density, safety, and cycle life. You don't need to memorize each chemistry in detail. Just understand that different cathode materials balance power, safety, and cost, depending on their structure and application. Future of lithium systems. Li-S batteries, one of two. Here we're looking at lithium-sulfur, Li-S batteries, one of the most promising next-generation lithium systems. These use sulfur as the cathode and lithium metal as the anode, offering a theoretical specific energy above 3,800 Wh/kg, watt-hour per kilogram, much higher than today's Li-ion cells. Sulfur is also cheap, lightweight, and environmentally friendly, making this technology attractive for large-scale applications. However, Li-S batteries face significant challenges that limit commercialization. The polysulfide shuttle effect occurs when dissolved sulfur compounds move between electrodes, causing capacity fading, low conductivity, and volume expansion during cycling. Dendrite formation on the lithium anode can lead to short circuits. The table summarizes these major issues and their impact on performance, from voltage drop and low capacity to potential electrical shorting. As we move toward advanced EV and grid storage applications, solving these Li-S challenges is a key focus of current research. Future of lithium systems. Li-S batteries, slide 2 of 2. In this slide, we focus on one of the main challenges in lithium-sulfur Li-S batteries, the polysulfide dissolution problem. During discharge, sulfur reacts with lithium to form a series of lithium polysulfides, Li2S. Some of these intermediates, like Li2S4 to Li2S6, are soluble in the electrolyte. As they migrate between the electrodes, they cause what's called the polysulfide shuttle effect. This leads to loss of active sulfur, capacity fading, and increased internal resistance, which together shorten the battery's lifespan. The diagram here illustrates how sulfur species transition from insoluble to soluble forms during discharge and charge cycles. To address this, researchers are developing porous carbon hosts, protective coatings, and solid-state electrolytes that can trap or confine these polysulfides and improve battery stability. Future of lithium systems. Lithium-air, Li-air batteries. Now we move on to lithium-air batteries, often called Li-O2 batteries. These represent one of the most ambitious next-generation energy storage concepts, offering the highest theoretical specific energy, over 5,000 Wh/kg, which is even greater than that of Li-S systems. Unlike conventional cells, the cathode reactant, oxygen, isn't stored inside the battery. Instead, air is drawn in through openings during discharge, making the system lighter and more compact. However, Li-air batteries face serious challenges. Lithium metal reacts easily with oxygen and moisture, leading to side reactions, capacity loss, and instability. To prevent this, a solid electrolyte layer is required to separate the organic and aqueous regions and control unwanted reactions. The diagram shows the overall structure, from the lithium metal anode through the organic, solid, and aqueous electrolytes to the porous air cathode. While still experimental, Li-air batteries could one day redefine energy storage density if these technical hurdles are solved. Lithium-ion batteries. Cell components. Let's look at the key components and structures that make up a lithium-ion battery cell. Every Li-ion cell regardless of its shape or design, consists of the same core elements: a cathode, anode, separator, electrolyte, and current collectors, all sealed inside a protective casing. The cathode determines the voltage and capacity of the cell, typically made from lithium metal oxides. The anode stores lithium ions during charging and releases them during discharge. The separator is a thin, porous membrane that prevents electrical shorting but allows the ions to move freely. The electrolyte acts as the medium that carries the ions between electrodes. Finally, the current collectors, aluminum for cathode and copper for anode, allow electrons to flow through the external circuit. The image shows four common cell formats: A. Coin type, used in small electronics; B. Cylindrical type, found in power tools and EVs; C. Prismatic type, used in automotive and energy storage systems; D. Pouch type, lightweight and flexible, popular in EV packs. Though their shapes differ, the internal electrochemistry is the same. Lithium ions move between the anode and cathode, enabling efficient and rechargeable energy storage. Electrolyte of lithium-ion batteries. The electrolyte is one of the most critical parts of a lithium-ion battery. It's what allows lithium ions, Li, to move between the anode and cathode during charging and discharging, while preventing electrical short circuits. It's designed to be a good ionic conductor, but a poor electrical conductor, ensuring that only ions move through the electrolyte, not electrons. In most commercially ion batteries, the electrolyte is a liquid organic solution containing LiPF6 salt dissolved in a mixture of carbonates, such as ethylene carbonate, EC, and dimethyl carbonate, DMC. It provides high ion conductivity, chemical stability, and operates within a wide electrochemical window, 5V. There are three main types: liquid electrolytes, most common, used in current EV batteries; gel electrolytes, help reduce dendrite formation and improve safety; solid-state electrolytes, the next step in safety and energy density, used in future battery designs. In the image, you can see a comparison between a fuel cell and a lithium-ion battery, both of which rely on ionic movement through an electrolyte to generate or store energy. This highlights the electrolyte's essential role. It's the invisible bridge that makes energy flow possible. This concludes Lecture 2 of 3. Please proceed to Lecture 3 of 3 to continue.